Welcome to homework.
Hello everyone, today we're doing chapter 29, problem 40, and this problem asks us to draw the organic product for amino acid leucine is treated with each of these following reagents. So if we draw leucine, remember leucine one letter code is L, we draw leucine, you have 1, 2, 3, 4 bonds, or 4 carbons I should say. So if we were to take leucine and react it with the reagent in A, we see that we have an alcohol group and a protonated group. So we can see that we're going to have an acid-catalyzed esterification reaction occurring. So if I see what we have in leucine, well, what can react with a proton? Well, we can see this oxygen can be protonated, and then we can have acid-catalyzed esterification, replacing this OH group falling off as water and being replaced with this methanol group here. So the product of A would just be ester formation. Methox, 1 carbon methyl ester formation for A. And now if we go to B, we see that we're actually adding an acid chloride with a strong base or a good base. So we can see that we need to have a nucleophile to react with this electrophile that we presented here. And the base, what's the reason that we have a base here? Well, the base is going to make our nucleophile into a better nucleophile. So it's going to make it more electron rich. So you can imagine that this pyridine is going to rip off a proton from a potential nucleophile, electron rich nitrogen. So it's going to make this into an N minus, or depending on the pH of the solution, just a neutral N, which is going to be more acidic than a positively charged nitrogen. And now this strong nucleophile can go through an SN2 mechanism to attack this acid chloride carbonyl carbon to kick off your good leaving group being chlorine and yield an N-acetylated version of leucine. So now if I draw the product of B, we see that we have an N-acetylated leucine coming off the nitrogen of the backbone. In C, we see that this is the same protecting group, the phenyl protecting group for carboxylic acids in the synthesis of amino acid problems that we've done in the past in this chapter. So we see that what we're doing is a carboxylic acid protecting reaction here by addition of this phenyl group. In C, and now in D, we are adding an anhydride, an acetic anhydride group. And once again, this is going to act as an electrophile. Remember, just like in B, when we reacted this leucine with electrophile, we added pyridine to make the nucleophile on leucine a stronger nuke, so it could attack this electrophile of the reagent D to give us some sort of product. So here, we see that we're going to have an acetyl nitrogen here. Protecting this nitrogen to make sure that this carboxylic acid stays highly reactive while deactivating the nitrogen of the backbone. Now in E, we're adding 1 equivalent of HCl. So 1 equivalent of HCl is going to protonate ionizable group. So everything here is already protonated except this nitrogen. So this nitrogen is the only thing that can be protonated here. So we're going to protonate nitrogen because it acts as a base. It's happy to be protonated and pick up that extra proton. To give us product E. Now product F, we're adding a strong base. So now we're going to deprotonate something that is easily deprotonated. So if I were to decrease the amount of protons in a solution or increase the pH, which one of these groups would lose its proton first? Well, the one with the lowest pKa. So if I were to raise a pH of the solution, anything above 2 or 3, then the first thing that's going to be deprotonated is this carboxylic acid. So we're going to deprotonate this carboxylic acid while leaving this amine alone, like how it is in the starting material in the question stem. So now we deprotonate this carboxylic acid while not touching this already deprotonated amine. In F, now we have a benzoic acid group, an acid chloride off a benzene ring with the same pyridine reagent. So we know that this is going to be an electrophile reacting with the nitrogen nucleophile off of leucine, and we know that there's going to be some sort of protection of this backbone nitrogen occurring, just like in a previous. So if I were to draw the backbone and draw leucine, now if I just imagine nitrogen is going to attack the carbonyl carbon and eventually kick off the chlorine leaving group, then we'll be left with this protecting group right here, being this benzoic acid group, 4G. And now in H, we see that we're adding Bock anhydride, so we're adding Bock anhydride and the base triethylamine. So once again, this is another amine protecting reagent that we use in the synthesis of dipeptides or peptides when you start with just amino acid building blocks. So in H, now the nitrogen here, the nitrogen is now going to be Bock protected, rendering it inactive and making this carboxylic acid the only reactive functional group in this amino acid. And now if we see an I, well, I says use a product in D and then add this functional group here. Let's see what D is. So D, we deactivated this amine group, so we're adding DCC and this peptide or this amino acid. And if I were to draw this amino acid out, let's just see how it looks like, because we're using it for I and J. Let's see. So we have this kind of amino acid derivative here. It's a glycine derivative. And we're adding DCC. So DCC is an amide coupling bond reagent. So it catalyzes amide bond formation. So in D, we inactivated the nitrogen. So we only have this carboxylic acid available for reactivity. And in the reagent I, we have this free amino group. So we're going to make an amide bond between this carboxylic acid and this nitrogen amine. And we're going to be using, obviously, the product in D. So let's go ahead and do that. So if I were to draw D out, so this is I. So if I were to draw D out, now we're going to form an amide bond using DCC amide bond coupling reagent to form product I. And on product J, it says use a product in H and add the same amino acid derivative and amide coupling reagent DCC. So the product in H is now, instead of an acyl protected amino acid or leucine, we're having a Bock protected leucine, but it's exactly the same thing. The only thing that's changing is the identity of your protecting group. So now in this case, we're just going to have Bock nitrogen to give us product H. Now in K, we're starting with original leucine and adding FMOC and carbonic acid and water. So once again, FMOC is we see that this kind of gives us a hint in the question stem. We see FMOC is attached to chlorine. So chlorine, we know right away, is a good leaving group. So right away, this kind of tells us this is going to be an electrophile, because electrophiles always have to have a leaving group on it, because when you make a bond, you need to break a bond, and that bond that's going to be broken is going to be the bond that's attached to your good leaving group. That's one of the characteristics of being an electrophile. So we know that this is going to be an electrophile, so we know that the only nucleophile on leucine is going to be this nitrogen group. So we know that what's going to happen is that we're going to have this nitrogen attack this FMOC, making a bond. When you make a bond, you break a bond between the FMOC and chlorine will pop off. So then we'd essentially have an FMOC bonded to this nitrogen group. So you can imagine FMOC as being just another protecting group for your backbone nitrogen. So now you have FMOC bonded to nitrogen. For product K. And now for L, you have this kind of carbamate moiety here. And this is kind of where the memorization in organic chemistry comes in, because this mechanism is kind of convoluted. It's kind of hard to work through in a test. So this is kind of where time-saving strategies come on test-taking situations, where you just can remember when you see this reagent is going to cyclize to form this compound here. So this reagent is going to cyclize to form this compound with this thiourea bond here, and then this amide bond there, and your ring is going to be out here. And now the only variable that you need to memorize, or you need to kind of add on the test, is that your R group is attached to here. So you just need to change the identity of whatever your R group is to be attached to on this carbon. So we know that the R group of leucine is 4 carbons. We have 1, 2, 3, and the 4th one coming out this carbon here to give us product L.